Hi, my name is Zach Lynn, and today I will be teaching you about maglev trains and all the components that make up magnetic levitation. First, let's go over the physical concepts that culminated together to create magnetic levitation. The first major concept is electromagnetic induction, which was discovered by the British chemist and physicist Michael Faraday in 1831. Electromagnetic induction is a process by which a changing magnetic field induces a current in a conductive material. This is caused by what is known as magnetic flux. Magnetic flux is related to the cross-sectional area A of the conductive material that is intersected by the magnetic field lines and the strength of the magnetic field, B. This flux causes electrons in the conductor to flow in a way that creates a magnetic field that cancels out the flux. Next, we have superconductors. A superconductor conducts electricity without resistance. Basically, electrons are able to pass between atoms without any loss of heat, sound, or other forms of energy. However, this is really only achieved at very, very low temperatures, at which the material is in an extremely low energy state. Once the material reaches this critical temperature, it goes from being a normal conductor to a superconductor. Now that we know how induction and superconductors work, let's see how they can be put together to create magnetic levitation. Once a superconductor makes the transition to its superconducting state, it excludes any magnetic fields from its interior. This is called the Meissner effect. Due to its zero resistance, any attempt at magnetizing the superconductor will induce a current exactly counteracting the imposed field. This causes the magnetic field lines to bend around the superconductor. Because of this effect, a small magnet is able to hover above a superconductor supported only by the repulsive force. Once again, since there is no resistance, the levitating currents adjust immediately to maintain levitation. As we'll see later, this levitation eliminates contact friction, which is essential in reaching higher speeds. The picture to the right shows a small magnet floating above a yttrium-barium copper oxide superconductor. Now on to maglev trains. There are two main types of maglev trains, German and Japanese. German maglev trains use electromagnetic suspension to levitate their train carriage, a system they coined Transrapid. Japanese maglev trains, also known as bullet trains, use electrodynamic suspension, what this video cares about, which is more interesting to me because of its use of superconductors. Electrodynamic suspension, or EDS, uses supercooled, superconducting electromagnets located on a guideway to levitate the train nearly 4 inches. This system saves energy because it still conducts electricity even when power is off. However, the cost of keeping the magnets cold can cost a lot. Also, a potential drawback is that the high-intensity magnetic fields can be harmful to pacemakers and other magnetically sensitive devices, thereby requiring shielding of the passengers from the fields. Also, because the train has to be moving for current to be induced, at lower speeds these trains are unable to levitate and require tires to get started. Still, the basic elimination of friction allows the train to move at amazingly high speeds, with the fastest being clocked in at 361 miles per hour in Japan. The guideway consists of a series of coils on each side. The superconductor is positioned so that it passes right below the center of these coils. This slight asymmetry is required because it creates more flux in the lower half of each coil than the upper half, producing a current that generates the magnetic force used to levitate the train. As you can see in the diagram, the coils on each side are the opposites of each other. This is just to create balance in the poles and allow uniform levitation. The last and most important concept in maglev trains is getting the train to accelerate. The way that electrodynamic suspension goes about this is through a series of propulsion magnets. As the train moves along the guideway, it sends signals through the induced currents that tell the system to input alternating currents on each side of the guideway in order to produce alternating north and south poles, which work together to push and pull the superconducting magnets, thereby accelerating the train. As you have seen, magnetic levitation combines seemingly simple physical concepts to create lift. Maglev trains put magnetic levitation on a macro scale by using this lift to eliminate friction and increase max speeds. Other potential uses of magnetic levitation include floating cities, efficient wind power, magnetic bearings, and space launch systems. The latter could be very interesting to see, as Popular Mechanics estimates the magnets could allow us to accelerate a spacecraft up to 18,000 miles per hour, enough to send it to outer space without rocket fuel. However, right now it is much too expensive. Thank you for watching my video. I hope you enjoyed.